Hi guys, this is Professor Darush back with you, and this time I'm going to show you how you can solve modular arithmetic with exponentiation without even using Fermat's theorem or Euler's theorem. Here I stated both Fermat theorem, which is if you have two integers a and p is a prime, and such that a is not divisible by p, so we have a to the power p minus 1 is congruent or equivalent to 1 mod p. Now from Euler's theorem, this is what we have learned, that a to the power of phi n, which is equal to 1 mod n under the condition a and n are relatively prime, and the phi of n is Euler function or totient function. Now, in this, I want to show you, of course, if you are given problems that is close. I mean, we have solved some problems before using Fermat's theorem and Euler's theorem. Okay, but we could have problems that we could use simple mathematical or exponentiation work in order to find the answer. Okay, and sometimes, of course, it will be useful to use Fermat's theorem or Euler theorem. Okay, but let's take a look at this example here. Okay, so we have 3 to the power 10 mod 13. So the question is to simplify this one or find the congruent or simplify. So 3 to the power 10, of course, it's 3 multiplied by itself 10 times. Now if you want to find the actual number really here, is that, let me just show you with the calculator here. 3 raised to the power 10, look how large is the number. So when you multiply 3 by itself 10 times, it's 59,000. Okay, of course it's 59,000 is large, but it's not quite as large as we have seen other numbers. But let's say 3 to the power 10, and you want to solve it using some kind of exponentiation, factorization. So here you need to take a look at what is uh, the modulus here. So here 13, we're looking at 13. So basically we understood from before, from previous sessions, that this is represent mod 13. So we have 13 different digits starting from 0, 1. So they represent all the positive integer 0, 1, 2, all the way to 12, because that's 13. So this is the set of digits. Okay, so we have 13 digits in this case. Now the way that it's when you have like exponentiation like this, 3 to the power 10, of course you will factor it, but when you factor it, you have to take a deep look at 13, the number 13 here. So the number 13, so we are trying, that of course that if you have mod 13, mod 13 is equal to 0, because this is how we looked at it before. So again, we have a set of integers from 0, 1, 2, 3, all the way to 12, and this is the set of integers that represent the 13, the modulus 13. Now when it comes to 13, so here, so 13 is equivalent to 0. So this is exactly, so it's exactly like saying 13 divided by 13 is 1, and the remainder is 0. Okay, so we already went through this process before. So basically, when you try to factor the 3 to the power 10, of course 3 to the power 10, we can factor it using many different ways. We can say that it's 3 times 3 times 3 10 times, because this is power 1, you add it, so up to 10 times, so it will be 10. Or you can make it such that it's 3 to the power or 3 square times 3 square times 3 square times 3 square times 3 square, or you can do a mixed. Okay, you can do 3 to the power 3. You can do, of course, here 3 to the power 3, 3 to the power 3, 3 to the power 1, or you can have any combination: 3 to the power 3, 3 to the power 4, 3 to the power 3, and so on. So, but you know, when you try to factor it, you need to look at this here. This is very important. Okay, the clock, which is, again, it's like, this is the digital clock. This is the modularity here. Okay, so we need to, when we try to factor, okay, factoring it using the first one, which is 3 to the power 1. I mean, when you have mod 3 to the when you want to evaluate 3 mod 13, this will lead to 3. So this is not really helping. All right, so even when we have 3 square, we have 9. So we have 9 mod 13 is equal to 9. So it doesn't help, because, you know, it did not really simplify this very much. So this is not going, because this is going to give us 9. So it did not really simplify. But what is going to simplify, for example, here, when you have 3 to the power 3, which is equal to 3 times 3 times 3, which is 27. Now here we're talking business. So when we have 27 mod 13, so it's basically, you know, here again, when you rotate here, this is 13, then we have 26, and then this is 27. So 1 is congruent to 27. So 27, of course, we divide by 13 is 26, and the remainder is 1. So this will make sense to us in terms of factorization. So when we have, it's better to use 3 to the power 3. Okay, 3 to the power 3. And notice that when we do the mod 13 for these, you know, this is 27. So basically they will go to 1. So it will become 1. So this is 1, and this is 1, and this is 1, and the answer is 3. Okay, so in this case we were able to solve the first problem. Okay, all right, so again, when you try to perform factorization, or trying to simplify, or to find the congruent for large exponents, then you have to take into consideration the modulus itself. All right, so let me erase this side here so I can go to the next part. So I'm erasing here. Okay, probably because, you know, I have my eraser is. All right, so I'll erase. Okay, let me see. There's another quick way for erasing here. That. Yeah, I think this is better. All right, so the next question here, or the next example that we're gonna go over with, and this is what we did in class, but I need to prove that these two numbers, or these two, are equivalent to each other, and they are going to be equal 16. So again, think about it this way. So again, I'm going to prove it. All right, so the question is that check if both of these formula or numbers are equivalent. Check if both are equivalent or congruent. So that's a question. So we have 3 to the power 12 mod 29. So now we have the modulus is different, 29, and here the modulus is 29. So both are modulus. So we are trying to see if those are congruent to each other, and simplify with simplification. Now it is similar to the previous one. Of course, first of all, I cannot use really Fermat's theorem in this case, or Euler's theorem. Okay, the reason why, the modulus is very large. Okay, so this is 29, so, and this is here, this is 12, but of course, 3 doesn't divide, or is not divisible by p, so yes, it's valid here. The same thing, 7 is not divisible by 29, and 29 is a prime actually. But I mean, using Fermat or Euler's theorem, it will complicate things, so let's do kind of simplification of exponents. And in this case, again, it's the same as we did in number 1. So let's take a look at number 2 here. So we have 3 to the power 12 mod, or module 29. So the same thing, we need to look at when we try to factorize 3 to the power 12 using exponents. So we don't want to use 3 to the power 1. We don't want to use 3 to the power 2, because 3 to the power 1 is 3. 3 to the power 2 is 9. 9 is very much less than 29, so it's not going to help us. Then 3 to the power 3 is 27. 27 is less than 27, so it's not going to help us as well. So, but what's going to help us is actually 3 to the power 4, for example. 3 to the power 4, it will be useful for us, okay? And 3 to the power 4 is, let's see here, 3 to the power 4 is equal to 81. All right, so this is going to be useful to us, all right, within that context. All right, so, and I don't know, I also use 3 to the power 5. Okay, so here in this case I use 3 to the power 5 for similar reason. Okay, but because I want it to be to have it large. Again, 3 to the power 5, the actual number here is 243. Okay, so I used 243, and I could have used also 3 to the power 4. If I use 3 to the power 4, so basically I will do 3 to the power 4 times 3 to the power 4 times 3 to the power 4, and this could be as well, it could work as well. Okay, so let's, I mean, since in this example I'm using 3 to the power 5, which is 3 to the power 5 is 243. So basically 243 mod 29. And when you try to find out the remainder, of course, here, so basically, 3 to the power 5 is 243. So basically you want to see how many 29s you have. You have 29 times, is it 3, is it 4, is it 5? So 29 times what? That will be less than 243. So obviously it's if it's 10, it will be 290. If it is 9, it will be still larger than this. So I think it will be 29 times 8. 29 times 8 actually. This will give us 72. And 8 times 2 is 16, is 23. So 232, and obviously here the remainder, okay, is equal to 11. And actually this is how we got it. We got the 11 here, and we got the 11 here. Now 3 to the power 3 squared is 9, so that's 9. Okay, again, this is one way to solve it. Now I'm not saying this is the only way. But again, when we look at 11, again the same thing. We can multiply 11 times 11. So 11 times 11 is equal to 123. And you want to find out how many 29s in that. So it's 29 times 4. Okay, if we multiply by 4, it's like 120. So this is actually, okay, because this is here 4 times 9 is 6, and 3, it will be 116. So when we try to find the remainder between these, so the remainder is actually 7. So the remainder in this case, it is 7. Let me just make sure. Again, 4 times 9 is 36. 6 plus 3, 4 times 2 is 11, so 116. And you got 4 plus 3 because the answer is, yeah, well, actually, well, I made a mistake. This is actually 121. So 1 or 11, this is here. 11 times 11, it's 11, it's 121. So I made a mistake before. All right, so let me just erase this one. So this is 121. So that's why the remainder is, let me erase this again. The remainder is 5. And that's why we get, when we did these together, it's 129 and 121. And when you do the remainder is going to be 5. Then we have 5 times 9, which is 45, mod 9, which is 16. That's how we got the 16. So this is the first part here. All right, so this is for the first part. So we found that 3 to the power 12 is equal to 16 mod 29. Now for 7 to the power 5, how to find out 7 to the power 5? Again, it's the same concept here. We need to use the exponentiation. So it is 7 to the power 5 is just like saying 7 to the 7 squared times 7 squared times 7, which is when you this is actually 1. So when you add all the exponent is equal to 5. So we can start with that as well. So we have 7 squared, which is 49, and basically this will give you the remainder is 20. The remainder is 20, and this is 7. So this is okay so far. Then we have, of course, when you multiply 20 times 20 will give us 400. And then the same thing here, we want to represent 400, okay, using some kind of multiplier of 9 plus the remainder. Now when we multiply this again, we found out, of course, by dividing by so it's equal to 12. Okay, so 12. So again, this is multiplication. So 12, of course, you know how to do it. Of course, you can divide it or you can multiply it, you can verify it. So anyway, 29, let me just verify it, times 12 is 18. This is 5, then 29. You add them up, that's 8, 14, 348. So 348, is this correct? Just double check it. 2 times 9 is 18. That's 5. Then we have 29. Then 8. And 9 plus 5, 14. That's 3. So probably then this is not correct actually. So I could have another 29. So it's actually 13. So let me just do 29 times 13. Alright, so it's basically 7, 2 here, 3 times 2, 6, that's 8. And then we have 29, and 7, 17, 377. This is actually works better because then the remainder is 23 in this case. Yes, the remainder is 23. So this is my mistake. So it's not 12, it's 13. So this should be adjusted to 13, and this would be 13, and the remainder is actually 23. This is exactly what I did, because this is when you do the module of this number here. So 29 times any number, of course, again, is gonna go back to 0 because the remainder here is 0, and this is 23 is left. So then what we end up with 23 times 27, and 23 times 27 mod 29. So basically here we because we have two numbers, we have 7 7 mod 29 is, so actually we have to multiply it. Okay, all right, so let me just erase here. So that's 29 times 5 plus 23. Okay, so that's 23. So this is here. It's let me just correct this one here, and I'm gonna erase. So this is already, we double checked it. Okay, so this is correct. So it's actually 400 is equal to 29 times 13, and I corrected my equation, and the remainder is 23, and this is here valid. And remember, it's dot 7. So again, I'm starting at the top again. So let me just change the color. Okay, now here again, I'm starting here, so I'm moving all the way here. So then we have 23 multiplied by 7 mod 29. So again, when you multiply 7 times 23, so this will give us 21. This is 2. 7 times 2 is 14, and that's 16. So it's 161 mod 29, and obviously then we'll try to factor it with respect to 29. So how many 29s do we have here? It is it 3? No, it is 4. It is 5.5. Okay, so let me just verify if it is 5. So 29 times 5, which is 45. So that's 5 plus 4. That's 145, and the remainder is 16 plus 16 mod 29. So obviously this is going to go to 0, and the answer is going to be 16. So the answer is 16 mod 29. So this is the answer. Let me just circle it with a different color just to make sure. So we proved the formula already, because this is here the answer and coincide with this one here. So they both are equivalent. Alright, and we were able to do it using exponentiation and factorization process. Okay, and thank you guys. See you next video. Have a good day.